Okay, so this test, the last one for the semester from me, was actually answered very well. The first question was, of course, the Zimmerman-Traxler transition state that you needed to do, and the only difference is I said that we're going to be using the trans enolate. Note that the formation of trans enolate over here is going to be, it's not going to be really good. There's going to be a bit of quite a mixture in this case. We only dealt with the chemistry in class today on how we would actually form that selectively using boron chemistry. Nevertheless, as we fill in the Zimmerman-Traxler transition state, essentially what we need to do is just lightly sketch out a cyclohexane chair, and then we fit all the little bits and pieces in. So we have our enolate at the back over there, we have our aldehyde over here, and we can just simplify this whole group over here, which comes out equatorially in the Zimmerman-Traxler transition state. This is where the reaction is going to occur. And we can just simplify it as an R group. And just note here that this is equatorial. Okay, that's just important. So I know that you're doing that purposefully. And then on the enolate, it's got to be the trans enolate. We've got an ethyl group over there, and the methyl group is on the same side. So it's over here. Same side as the ethyl group on opposite sides to the oxygen. All right, and so of course we've got a hydrogen going down. So the reaction occurs, the minus over here, enolate aldol reaction, and the result of that is, again, we draw out a nice little chair. It's a good idea just to sketch these out loosely, but at the same time, when you sketch them out loosely in pencil, just to do it neatly, make sure that you erase unnecessary bonds. For instance, this over here is where the reaction was occurring, so you don't have that as a solid line going across, because only after the reaction is it a solid line like that, and we can keep it in. So lithium, oxygen, ethyl, methyl, hydrogen, and our R group that is coming out like that. All right, and so if we, now we've got our product over there, which of course will be protonated in workup. If we expand this out in the zigzag that we have, we've got the ethyl zigzag, zigzag. This is the plane over here of the product. As we look at that, this methyl group is actually facing up and this one is facing down. So if we drew out the product in the same way as it's drawn at the top, we actually see that the methyl group is pointing up and the new OH that we formed is going to be pointing down. So let's try to phenyl there. And of course this is racemic. So this would be the correct enantiomer as I've drawn out over here, but of course remember that this reaction is not enantioselective, just diastereoselective for the anti. In this case we got the anti, so we must put the plus minus there to tell me as the examiner that you understand that. All right, and the second question was a cram chelate model, so not the Felkin-On. A lot of you started writing stuff about Felkin-On and that wasn't necessary. What we need to do is we need to stick our eye down this bond over there. So when we draw that out, and again, a lot of you got this, had done this very well, and so well done on that. This big aromatic group over here, right, is over there, and we've got the methoxy on this side, and hydrogen on this side over there. So this side over here is the top face and this one is the bottom. All right, but now in the cram chelate model, because we've got magnesium, and that's why I told you that in the exam you wouldn't be told, you need to know this, these two oxygens are going to be connected to each other. So there's only a minor change now in the structure when we apply the cram chelate model. All we're doing is bringing that OMe a little closer, and let's just show the magnesium. One of you used zinc. I'm not too sure where the zinc came from, but anyway. Aromatic, and the hydrogens over there. So the preferred attack is going to be from here. This is, so we write there, preferred attack, least sterically hindered, and of course this is the Berge done its sorry, angle, which is 107 degrees, is fine. All right, so just mention all that. All right, so we've got that. Now I've got 3 marks. We haven't got to the final product over here. A lot of you made the mistake I said you need to be careful of. It's coming in from this side, which is the bottom face. It means that the ethyl is going to be pointing down. So when we draw out the product, so we draw out our aromatic, don't forget the nitro. Okay, so the methoxy. Right. We've got a hydrogen in there. We're going to keep the hydrogen in the plane. So the oxygen, if the ethyl comes in from below, the oxygen is going to point up, OH, and the ethyl will be pointing down. And that would be the correct answer. And you could stop at this point. If you spin this round, all right, we twist it to get to something like that, you'll actually see that the OH still remains pointing up. You might need to use a molecular model to see that if you're not seeing it straight away, but this would have been correct and you would have got your 4 marks. Okay, good.